In this video, we're going to talk about hypothesis testing for a proportion. Let's start with an example. Suppose a coin is tossed 100 times and there are only 41 tails. Is this enough to argue that the coin is weighted towards heads? So how would we argue this? One way we could do it is say, okay, well, if the coin was fair, what is the probability of 41 heads or fewer? What is the probability of a result at least this extreme? So our argument to show the coin is unfair or find out that it isn't, either way, is to say, okay, assuming the coin is fair, making that assumption, what is the probability of a result at least that extreme? And if it's very unlikely, if it's an unlikely result, then we'll say, okay, that tells us the coin is not fair. If it's not that unlikely, then we'll say, okay, we have not proven that the coin is unfair. So what cutoff point should we use for how unlikely something is? That will depend on the scenario. But in this example, let's use the cutoff occurs less than 5% of the time, or we're using a cutoff of 0.05. So if our probability of a result at least this extreme ends up being less than 0.05, then we'll say, okay, that's enough to say that we really believe this coin is unfair. It's unfairly weighted towards heads. And if the probability of a result at least this extreme is not less than 0.05, then we'll say we do not have enough evidence to say that this coin is weighted towards heads. We do not have enough evidence to say that this coin is unfair. So, okay, let's find this probability. What is the probability of 41 or fewer tails in 100 tosses? So one way we could do this is use a binomial distribution. This is a classic binomial distribution. Successes and failures, heads and tails. Probability of success in one trial is 0.5. And if we did that, we could say, okay, what's the probability that there are 41 or fewer heads, 41 or fewer tails? That's the probability that there are 0 plus the probability that there's 1 plus ... the probability that there's 41 of them. So that's one approach. But we want to have a general approach. I mean, first of all, that looks annoying to add up. So what we want to do is have a more general approach that could work for really large sample sizes. To do that, we're going to use the central limit theorem. And by the central limit theorem, we know that sample means are approximated by a normal distribution. And as we said in a previous video, a sample proportion really is a sample mean. So a sample proportion, you could think of it as yeses are ones, nos are zeros, or, tails are ones, heads are zeros, and you're adding all those up and dividing by the number of trials. And so that really is a sample average, a sample mean. So sample proportions of size n with probability of success p are approximately normally distributed, and the mean is just the proportion of successes that we expect. And the standard deviation is the square root of p, the probability of success, times 1 minus p, the probability of failure, divided by n, the sample size, all under the same square root. So we want to find the probability that our sample proportion is less than 0.41, that there are fewer than 40 or less than or equal to 41 heads in 100 tosses. So this is our sample proportion. In this case, it's the number of tails over the number of tosses, coin tosses. And so that was 41 over 100. That's 0.41. And that's our sample proportion. As before, we're going to label that as P with a hat, the sample proportion, as compared with P, which is the expected proportion. So that's our expected proportion if the coin was fair. So we're assuming the coin is fair. What's the probability of getting a sample proportion of 0.41 or less, assuming that the coin was fair? This is now normally distributed. It's normally distributed, again, with our mean of P is 0.5. we expect that in this case, heads and tails are equally likely, so 0.5 would be the expected proportion. And the standard deviation is the square root of above p times 1 minus p over n, so that's 0.5 times 0.5 divided by 100 is the sample size. And so if we do that calculation, we'll end up with a standard deviation of 0.05. So we're looking for the probability that here we've got a mean 0.5 and a standard deviation of, in this case, 0.05, and this is normally distributed, the probability of a result of 0.41 or less. So we did problems like this before where we found probabilities for the normal distribution. We did this in two different ways. One was to use a computational device with that mean and that standard deviation. Another was to find the z-score and then use the table. So I'll do it that way in this case. The z-score, remember, is our data value minus the mean divided by the standard deviation. For us, that's the sample proportion minus the proportion we expect over this, standard deviation is square root of p times 1 minus p over n. So here, that's the sample proportion, 0.41 minus 0.05 divided by 0.05 was that standard deviation of these sample proportions. And so that's negative 0.09 over 0.05, that's negative 1.8. So our z-score is negative 1.8. We can then use the standard normal table to find the probability that z is less than negative 1.8. So the probability that the sample proportion is less than or equal to 0.41 is equal to the probability that z is less than or equal to negative 1.8. And looking that up in the z-score chart in the standard normal table will give us a probability of 0.0359. 0.0359. That's just looking that up in the table. And that is the probability that we're looking for, the probability that the sample proportion is less than 0.41. All right, let's think back to what we were doing. So a coin is tossed 100 times, there are only 41 tails. Is this enough to show that the coin is unfairly weighted towards heads? To show that, we would say, assuming the coin was fair, assuming that the true proportion of heads and tails is each 0.5, that they're equally likely, we want to show that a result at least this extreme, in other words, the probability that the sample proportion p hat is less than or equal to 0.41 is very unlikely. How unlikely? Occurs less than 5% of the time, is less than 0.05. Have we done that? Yes, we have in this example. So we showed that the probability that the sample proportion is less than or equal to 0.41 is equal to 0.0359, and that is less than 0.05. That was less than our cutoff of 5%. So this is enough to, this argues that the coin is weighted against tails, weighted towards heads. So the procedure described above is hypothesis testing. Now let's talk about this in terms of the language of hypothesis testing. So hypothesis testing always has two hypotheses, the null hypothesis and the alternative hypothesis. The null hypothesis is typically like nothing has changed or the status quo is still true, and this is usually denoted by HO. The alternative hypothesis is what we're testing. It's usually something has changed or something is different than expected. And some, books or, papers or researchers call this HA, the alternative hypothesis, and others call it H1, H0, H1. And you can use either. So in our case, the alternative hypothesis, what we were testing is that the probability of tails is less than 0.5, right? We were testing for that. And we were testing to see, is this enough to say that the true probability of tails for this coin is less than 50-50, is less than 0.5? So we could also write that as probability of tails is less than 0.5, or this is sometimes just written as p less than 0.5. Now for the null hypothesis, there's again different ways we could say this. One is to say that that this coin is fair. Nothing has changed. The status quo, what you expect out of the coin, is true. Another way to say it is that p is equal to 0.5, that heads and tails are equally likely. And depending on, again, the resource that you're using, the paper, etc., we sometimes do either, in this case for what's a one-tailed test, we can either do p equals 0.5 as our null hypothesis, or p greater than or equal to 0.5. The reason we would use this is that sometimes we like the null hypothesis to be the complement of the alternative hypothesis. Not a very big deal. I'm okay with either of these situations. In hypothesis testing, we assume the null hypothesis is true. That's what we did above. We found this probability based on the assumption that the true proportion for the coin was 0.5. We found the probability of 41 heads or fewer of a sample proportion of 0.41 or less based on assuming that this null hypothesis was true. We then collect or observe data, in this case 100 coin flips, 41 of them were tails, and find the result of the probability of a result that extreme or more extreme than the one we observed. That's what we did. We found the probability that the sample proportion is less than or equal to 0.41. And if the probability of such a result is very small, we reject the null hypothesis. In this case, we did that. We did reject the null hypothesis. We found that the probability that the sample proportion was less than or equal to 0.41 was 0.0359. So that was the probability of a result at that extreme or more extreme. And because of that, we said, yes, this is enough evidence to say the null hypothesis is false, that we are rejecting the null hypothesis. So that's what happened in this case. If the p-value is not very small, if we didn't have that situation, if we found out that the probability of an event was, 0.2 or 0.3 or something like that, not very small, then in that case, we do not reject the null hypothesis. And this is some double negative stuff going on here. There's a lot of that with hypothesis testing language. So we do not reject the null hypothesis. Say we went through that process and we found that the probability of a sample proportion that small or smaller was like maybe 0.07, happens 7% of the time. Then we might still say, hey, I kind of think the coin is unfair still, but I didn't prove it exactly. I didn't get a result that was a probability that was smaller than 0.05, than 5%. So I didn't prove the alternative hypothesis. I was not able to reject the null hypothesis, but I'm not exactly accepting the null hypothesis either. So that's typically the language that's used. Instead of accepting the null hypothesis, you're just not rejecting the null hypothesis. We do not have enough evidence to say that the null hypothesis is false or that something has changed. Some more language. The p-value is the probability of a result at least this extreme, assuming the null hypothesis was true. In our case, the p-value was what we observed, the probability that the sample proportion is less than or equal to 0.41, and we calculated that to be 0.0359. And the cutoff mark for p-values is called the level of significance. And that's called alpha, the level of significance. That's a Greek letter, alpha. Alpha. It's a Greek letter. It looks like a fish swimming that way. In our case, alpha was 0.05. That was the cutoff point. And we said that if the p-value was less than alpha, we would reject the null hypothesis. if the p-value was greater than or equal to alpha, we do not reject that null hypothesis. So if the p-value is less than alpha, the level of significance, we reject the null hypothesis. If the p-value is greater than or equal to alpha, the level of significance, we do not reject the null hypothesis. We used a level of significance of alpha equals 0.05, but alpha equals 0.01 and alpha equals 0.1 are also used. This is the most common, but we might use 0.01 if we want to be absolutely certain, maybe if it's a very important medical trial, or we could use alpha equals 0.1 if it's hard to get a large sample size. So for example, like say some educational studies over a long period of time, if it's hard to get a large sample, you might use alpha equals 10% or 0.1. The test we did above is called a one-tailed test. It's called a one-tailed test because we were testing specifically whether the coin was weighted towards heads. So if P is probability of tails, we were testing whether P was less than 0.5. But what if we instead wanted to test whether P was just not equal to 0.5 in either direction? Just the coin was unfair in one way or the other. So this would be one-tailed when we were tested if the probability of tails was less than 0.5 versus if we were testing whether probability of tails was just different than 0.5, then that would be a two-tailed test. And in that case, then the alternative hypothesis, probability the proportion of tails is not equal to 0.5 would be our alternative hypothesis, whereas the null hypothesis would be just the proportion of tails is equal to exactly 0.5. So again, before we were only interested in finding a result at least as extreme as 0.41. So we were trying to find a result, the probability of a result at least that extreme, assuming that the coin was fairly weighted, that P was truly 0.5. Now, because we are interested in both tails, we want to find the probability of a result at least that extreme on either end. So the probability that it's less than 0.41 on that end, or greater than, so this is a difference of 0.09, this would be greater than 0.59 on that end. So if we're talking about a two-tailed test, remember with the normal distribution, these little pieces are called tails, then we're looking for the probability of a result at least that extreme in either direction. In either direction. So here we would be looking for the probability that the sample proportion was less than 0.41, or the probability that, so plus the probability that the sample proportion is greater than 0.59. So what is that equal to? Well, we already figured out that the probability of this, the probability that the sample proportion is less than 0.41 was 0.0359. 0.0359. So what is it over here? Well, it's the same thing, right? Because we know that the normal distribution is symmetric, and so it's going to be the same thing in both tails. So the only thing that changes when we do a two-tailed test is that the p-value is going to be twice what we get in one tail. So we can still calculate that value for one tail, and so this time it would be 2 times the probability that the sample proportion was less than 0.41. That's 2 times 0.0359. And so if we multiply that out, we get 0.0708. So 0.0708 would be our p-value if we were doing a two-tailed test, just saying, is this coin skewed one way or the other? And in this case, since the p-value is equal to 0.0708, is greater than alpha, the level of significance, 0.05 level of significance. Remember, that's the cutoff point significance. the cutoff point for determining whether something is unlikely enough to reject the null hypothesis. Here, the p-value is greater than that, so we do not reject the null hypothesis in this case. We do not reject the null hypothesis because this event was not unlikely enough to say it happens less than 5% of the time, which was our cutoff point in this case.